Okay, so I think it's time. Welcome, everyone. I am Mateusz Jurczyk, and today I will be talking about effective file format fuzzing, specifically some of the techniques, methods, and the results that I've had during the few years of fuzzing that I've been doing at Google. So a few words about myself. I work at Project Zero. What is relevant to the talk is that I am a part-time developer and a frequent user of the fuzzing infrastructure that we have there internally. And it is very related to what I will be discussing here today. I also play CDFs and I'm generally interested in all sorts of vulnerability research and software exploitation. So today I will be talking about what constitutes real-life offensive fuzzing. So fuzzing for actually finding bugs that you can probably exploit, or in my case, report to the vendors. And I would like to talk about how each of the stages that is part of fuzzing is typically implemented and what you can do better to actually improve your results and find more bugs. And so this is going to be all shown on the example of several different pieces of software that I have fuzzed in the past, including Adobe Reader, Adobe Flash, Windows kernel, and some other open source software. So let's start with some very soft basics. We probably know what fuzzing is. So it's just a software testing technique, which is most often automated. And it's all about just feeding invalid data to the software that we are testing. So in the case of my talk, the software part is just commonly used programs and libraries, which can be both open and closed source. The important thing is that they are written in native languages. And this means that they can be used for memory corruption style zero-day attacks. And on the other hand, the inputs are just, we assume that they are files of different structure, which may be documented or undocumented, and they are processed by the software. So that they can be websites, applets, images, videos, and stuff like that. So in general, the scheme of fuzzing is very simple. We just have a loop inside of which we choose an input, mutate it, feed it to the target, and then see if the target has actually crashed or not. If it has, we save the input, and if it hasn't, then we just proceed. Of course, this is still very simple. But while the general scheme is very easy, it's the thing that is easy to learn, but it's more hard to master. So if we try to dig deep into how to fuzz effectively, we have several questions that we have to answer. So you have to think about how we choose the fuzzing target in the first place, how we generate the inputs, where do we take them from, if we have some base corpus, how do we mutate them, and there is like a huge list of things that we actually have to consider. Some of these things are taken care of by the fuzzer that we are using if we use an off-the-shelf one. But if we are trying to create a fuzzing system on our own for whatever reason, then we actually have to think about all of those things. So I will discuss some of those things and try to answer to the best of my knowledge how to make them as effective as possible. So let's start with gathering the initial corpus of input files. Probably most people doing fuzzing actually go through this step because it is a desired step in a majority of cases for several reasons. Of course, it makes it possible to reach some code paths immediately after starting the fuzzing, so we don't have to recover all of this file structure by ourselves. We already have a good starting point. We may have some complex data structure inside of those files, which could be either very difficult or impossible to generate, even if we have code coverage information available. And even if these constructs could be created by, for example, using code coverage-based fuzzing, we are still saving a lot of time by doing the initial corpus generation. And of course, if we have a specific corpus of files in a format, such as, for example, PDF, we can reuse the same corpus to fuzz different projects afterwards. So the standard methods of doing this is as follows. First of all, many open source projects actually already include extensive sets of input data for testing that we can use. For example, the FFmpeg project, which is a video and media processing library, has something called FFmpeg Fate, and it's a system for regression testing in FFmpeg, and it already has like hundreds of interesting files that you can use. Sometimes these files are not publicly for everyone, but if you reach out to the developers and let them know that you want to test their software. They might be happy to share some of their private samples with you. And also many of the projects, especially the open source one, actually include converters from format X to their own format Y. And the example here would be the WebP image format, which has a converter called CWebP, which can convert from PNG, JPEG, and TIFF. Another thing that we could do is internet crawling. So it also, of course, depends on the popularity of the fast file format, but it's quite an intuitive approach. So we could either just download files with a specific file extension or with a specific magic bytes or some other way of recognizing those files. The problem is that if we are targeting a very popular file format, we can end up with terabytes of data, but it's not really a problem if we can distill it to a reasonable corpus somehow. But another interesting idea is that we could actually try to ask the actual target what it thinks, whether it thinks that it supports the specific file or not. So this could be either achieved by using code coverage again, but this tends to slow down the process very much. But in some cases, you can just directly ask the question to the program itself. And the case study here would be IDA Pro. So as you probably know, IDA Pro has a long list of supported formats. This is not the complete list, but it's already a lot of items here, probably several dozens of them. And so when you try to load a file in IDA, what happens first is you see this window which lists all of the formats that it has recognized inside of the file, and you can choose how to load this file. But the real question is, how does this really work? And to find out about it, you have to look into the loader architecture in IDA. And it turns out after a few minutes that they have a modular design with each loader being inside of a separate file. So inside of your installation directory, you have a long list of files, which are basically just DLLs or shared objects or some other file depending on the architecture, which exports two functions, accept file and load file. And you have two versions of each of those files for 32-bit and 64-bit version of IDA. So the definitions of those two functions you can see here. They are also documented in the IDA SDK. They are very simple. They just take some input stream and output some information about the file. So accept file is basically the function which performs some very preliminary processing, and it returns 0 and 1 depending on whether IDA can actually handle this file or not. And load file is the more complicated function which actually takes care of the regular processing of the file when you decide to load the file. And yeah, as I said, both functions are very well documented. And this is very convenient for us. So when I was fuzzing IDA myself, I decided that I could just write a simple loader which would iterate through all of those loaders, call the accept file function, and see which file it would recognize. So here you can see an example of running the loader against itself, and you can see that elf.llx actually recognized the file as elf, which is correct. So this was very helpful to actually, from a large corpus of files, see which files would be handled by IDA correctly without doing all those code coverage, information extraction, or anything more complicated like that. So this was very good because it worked with a very high degree of confidence, because the accept file function actually has some extensive logic to determine whether the file should be accepted or not. Thanks to this, we also knew that which loader exactly would be able to load. So we would know which loader we would be able to find bugs in using the specific file. We didn't really have to even start IDA, because we would just call a simple function from a single DLL or shared object, and we didn't have to use any instrumentation. So similar techniques could probably be used for software, which makes it possible to quickly determine whether it supports the specific file or not, which can be useful sometimes. So the other thing is, after we already try to get like the initial large set of files, is that we could try to distill it. And I believe that in fuzzing it is quite important to get rid of most of the redundancy in the input corpus. And this means both the first one that we actually start fuzzing with, and also the living one, which is being used while we do the fuzzing and evolve the corpus to get a better one. So in the context of a single test case, we want to maximize the program states explored divided by the input size, which means that we want to have the highest ratio of byte to program feature, basically. So the highest number of functionality starts by the smallest number of bytes. And likewise, in terms of the whole corpus, we also want to maximize the whole set of program states divided by the number of input samples, because we don't want to have too many of them exercising the same functionality. If there is too much data to actually process using corpus distillation with code coverage information, we may also try to write some kind of minimizer on our own based on the basic structure of the file. Some file formats have some basic structure, which is, for example, being divided into chunks that have tags or some names. This is the case for Swift files, PDFs, PNGs, and many other files that you can see out there. So such generic parsing can already be used to do some very quick preprocessing before we do anything more complex. But you have to be careful not to go too deep into the specifications, because then it gets harder and the result is not as cost effective as it is where we just do very basic processing. So now the question is, how do we actually define the program state? Because the file sizes and the cardinality, which was part of the expression, are both trivial to measure, but a program state is more difficult. So we don't really have any good metric for measuring program states, especially with the characteristics that we would like to have while doing fuzzing. So we would like the program state to be defined such that the number of them should be within a sane range. So we cannot really count all combinations of bits in memory. They should be meaningful in the context of memory safety, and we should be able to easily determine them during program runtime. So the most approximations used today are just assuming that code coverage is somewhat equal to program states. And of course, this has many advantages because, first of all, increased code coverage is representative of new program states, which is good for us. The sane range requirement is met, of course, because code coverage information is typically linear in size to the overall program size. And we can easily measure it using compiled and external instrumentation. But the disadvantages is that constant code coverage doesn't really indicate that the program state set is also constant. So we could be missing some information using this method. So yes, the current state of art is just counting basic blocks, and it's a reasonably good approximation because they have quite good granularity. We shouldn't really measure instructions typically because this is redundant information. So we can measure the code coverage of basic blocks using compiler instrumentation such as gcov or external instrumentation such as Intel Pin and DynamoRia, and just identify those basic blocks by the address of the first instruction. But the problem with this approach is that we could be still missing some information. So here we have a very simple program with a full function, which has a very simple if statement. So we have 3 calls of this function, and when we perform the first call, we actually go through all of the basic blocks through some of the edges. So we could think that we have the maximum coverage of this function as of now, but if we see this second call, we can see that a new path is actually being taken, a new branch here, and the same goes for the second call as well. So if we're just measuring the basic blocks, we could be missing this information. So another idea to approaching measuring code coverage would be to not measure basic blocks, so not the vertices of the graph of the code execution, but the edges. And this is, of course, what AFL is trying to do. So they were the first to introduce this and ship at large. And you can read in the technical white paper of AFL that they are noting the combination of the current location that is reached in the code and the previous location inside of the bitmap of all basic blocks. So yes. But we could also extend this idea even further. So in a more abstract sense, recording edges is recording the current block and the one previous, but we could also record even more information by tracking not the only previous block, but also more of them. So for example, n previous blocks and the current one, which would provide even more context as of how the program actually arrived at the current state. But in my experience, the direct edges are quite a good approximation because they are fast to determine, and they also they don't have too much redundancy. But yes, so you can also have even more granular information, such as counters and bit sets. So instead of just recording whether a specific basic block or edge has been reached or not, we can count how many times it has been reached or not. This can be useful, for example, when we try to determine how many times a specific loop has been has iterated over, which could be helpful, for example, in a case where we want to go through a string comparison or some other logic of that kind. So we have all these different kinds of coverage information that we would like to extract. Of course, we can do it using Intel Pin or DynamoRE or some other DBI. For example, AFL uses a modified version of QEmuser. For open source, we can use the built-in compiler instrumentation, such as gcov and llvmcov. But what I have been using personally and would recommend to use is sanitizer coverage. So sanitizer coverage is just an option of address sanitizer, which you are all probably familiar with, which is a fast, reliable instrumentation for detecting memory safety issues. So it's very useful for fuzzing by itself. There are also many other variants, such as memory sanitizer, thread sanitizer, etc. And one thing you can also enable while enabling other sanitizer is the sanitizer coverage, which at the same time as validating the runtime of the library or program, also provides information about the code coverage. So I am using it personally. Also, the libfuzzer project, which is the project of Kostya, who is the creator of other sanitizer, uses sanitizer coverage. Here we have an example of sanitizer coverage usage. So we have a very short program which has some foo function, which is only called if the number of parameters is 2. So you can just use two simple compile time options to enable it, and then you can see that after we call the program with 1 and 2 parameters, the size of the output files with the coverage information is different. It has either 4 or 8 bytes. So now that we can measure code coverage easily, the question is, what do we do now? First of all, we have to remember that just measuring code coverage by itself is not really a silver bullet. And there are still many code constructs which are impossible to cross with just dump mutation-based fuzzing. Examples of this would be comparisons of types that are larger than a single byte, for example, or comparisons of memory blobs or ASCII strings. So you can see those examples here. A comparison with a 32-bit value, of course, is a very difficult to cross with just a dump fuzzer, because we would have to guess this specific 32-bit value. And the same thing goes with the string comparison, which would be even harder to guess. So that problems are actually somewhat approachable if you think about it. Because you can, for example, use approaches such as dictionaries, which are supported in both AFL and libfuzzer, which could be used to find those specific values that are being searched for in the code. And you can also get some help from compiler flags, but this is somewhat complicated to think about, because the somewhat unintuitive approach would be to disable all code optimization, which would result in fewer hacky expressions in assembly, compressed code constructs, folded basic blocks, and stuff like that. So we'd get more granular code coverage information to analyze. But on the contrary, Elcam have also found that if you use the O3 optimization with unroll loops, then some of the short string comparisons or string signatures are being unrolled to just very simple byte granular comparisons. So it's quite unclear which compilations flags should really be used for coverage-guided fuzzing, and it's probably something that you should adjust based on the specific project that you are trying to fuzz. So in the past, also Tavis Ormandy tried to approach this problem somehow, with another DBI of his that he called deep cover analysis. So he tried to extract some more granular information about the specific instructions that are used for string comparisons, for example. So he implemented this to measure how far the execution of the rebs CMPB instruction went before bailing out, or how many bits were successfully compared by the CMP instruction. And he was able to use this approach to be able to actually recover CRC32 checksums required by the PNG decoders. And when I was first creating these slides a few months ago, I also thought that the ideal feature would be to have a specific compiler designed for fuzzing, which would be able to create very de-optimized code with all of the assembly being maximally simplified, with all of those 32-bit and 16-bit comparisons being unrolled to byte comparisons and stuff like that. So, for example, the construct on the left would be changed to the construct on the right. And it turned out that this has actually been achieved in the meanwhile. So in August, a research has been presented resulting in a LLVM compiler plugin that was actually able to perform these de-optimizations. And this helped AFL to discover several new bugs. And the other part of the ideal feature would be that the standard comparisons functions, which are very annoying, we could have a compiler-based solution for just having a separate version, a separate piece of code in the assembly for each of the calls of those functions in the code, which would help us get some more granular information as well. But we still have some unsolvable problems, such as when the value that are being loaded from the input is actually processed somehow before being compared with some signatures, and this we cannot really approach with any of the dump ideas that I presented before. But this is about dump fuzzing, so we have to just agree with that. So now that we have lots of input files, we have the compiled target and the ability to measure code coverage. The question is, how do we proceed from here? And this is assuming that we would like to create some corpus management system. I would like to present some algorithm of how I do it myself. So let's assume that we would like to have the system for coverage-guided corpus management, which would have the following properties. First of all, it would be able to minimize an initial corpus of potentially gigantic sizes to a smaller one that is equally useful. So on input, we would have n input files, and on output, we would have m input files and information about their code coverage. And of course, this should be scalable. This is the first property, and the second one is that we would also like to use it during fuzzing. First of all, to decide if a specific mutated sample should be added to the corpus at runtime, and to recalculate all of this coverage information if needed. So the input here would be just the current corpus and its coverage, and the candidate sample and its coverage. And on output, we just should have the new corpus and its coverage. So yes. The prior work for this is that the set cover problem, so this is the set cover problem or just a specific version of it, which in itself is just NP hard, so we cannot really calculate the optimal solution in reasonable time, but we don't really have to do it. And in fact, it's probably better if we just don't find the optimal solution, but a somewhat optimal one. And there are actually greedy algorithms which can find approximates in some reasonable time. An example of such an algorithm would be that we store the current corpus and the current coverage, and for every new sample, we just check if it adds some new trace to the current code coverage. So if it does, then we add it to the corpus, otherwise we discard it. And periodically, we could also optionally check if some of the samples are redundant inside of the corpus and remove them to keep the general size small. But this has some significant drawbacks. So for example, it doesn't scale very well because we have to process all of the samples sequentially. And also, The size and form of the corpus depends on the order in which the samples are processed. So if we start processing the big files at the beginning and then the smaller ones later, then we would end up with a very large corpus, which is not necessary. So we have very little control over the trade-off between volume and redundancy in the output corpus. So what I would like to propose is another design, which is as follows. For each execution trace we know, we store the n smallest samples which reach that trace, and the overall corpus consists of all the files present in the structure. And the structure can be represented as a C++ STL object map, which maps a string, which is the name of the sample, the name of the trace, into a set of pairs consisting of the names of the samples and its sizes. So here is an example on an illustration. We have four input samples which have some coverage, and then we transform it into a list of traces which map to a maximum of 2 files per that trace. And they are, of course, the smallest one here. So the advantages of this approach would be that this, of course, can be very trivially parallelized with any number of machines using the MapReduce model. The extent of redundancy can be controlled via the n parameter. During fuzzing, the corpus will evolve to minimize the average sample size by design because we are storing the n smallest samples. We have at least n samples for each trace, which results in a very uniform code coverage distribution across the entire set, as compared to just having like 1 samples per each trace. And the upper limit for the number of input is limited, but in practice it's much less than actually the number of coverage traces times n. This approach also has some shortcomings. So due to the fact that each trace has the smallest samples in the corpus, for some basic traces, we will end up with some redundant short files which don't really exercise any interesting functionality. For example, for PNG, we have some files which just have the basic headers and stuff like that, or just basic headers and then a single chunk. So very short files which aren't really useful for fuzzing. But I still think this is an acceptable trade-off, especially given that having such short inputs may also enable us to find some unexpected behavior, for example, also handling some other types of magics by the target that we didn't initially expect. So here is the algorithm in a kind of pseudocode. So the map phase is really simple. We just get the code coverage provided by the input data. And for each trace ID, we output the trace ID and the pair of sample ID and the size of the file. So here you can see it. We transform the list of the input files into a map of traces mapping to the samples. It first looks like this. And then for the reduce phase, we just sort for each of the traces, we just sort the list by the size of the samples and then choose the n smallest one and output them. So here we start with this input. We just sort the files by size and then we choose the n smallest ones, which in this case is 2. And this is our output. So at the end, we end up with this list of files at the top, and then we just sort it and get a new unique list, and we end up with a total of 3 out of 4 files in the initial corpus. So when it comes to the actual track record for using this algorithm in my infrastructure, I've successfully used it to distill data sets of terabytes to distill it into somewhat reasonable corpuses. And the examples are PDF format based on instrumented PDFium. So I generated 3 corpuses based on n equals 1, 10, and 100 to get some nice corpuses for fuzzing with different degree of redundancy. And I've done the same for free type too. So when it comes to the algorithm of determining whether a new candidate is good for fuzzing or not, the algorithm is a little bit more complex. First of all, we go through each of the trays which is covered by the sample and see if it improves the size of one of the traces. So if it's smaller than the size of the largest file in the set, And if any such improvement is achieved, then we perform a second pass to remove all files from the set which have the same size as this file. And here is an illustration of this approach. So we have this candidate called 5.pdf, which has size 20. So first thing we do is that we try to improve some of the covered traces here. And it turns out that two of them are improved. So we insert the 5.pdf file for two of the covered traces, and then we perform the second pass and also replace two other files which also had size 20 to reduce the total number of files in the set. So this was about distilling the whole corpus and merging in a single file. And if we want to merge two corpora, then it's also trivial by just choosing the smallest n samples for each of the traces that are covered by it. And one of the things that I fuzzed and had some success with using this approach was Wireshark, which I've been fuzzing since November last year, using the tshark command line utility built with ASAN and ASAN coverage. I discovered 35 vulnerabilities using this approach. And the interesting thing is that initially I started with some simple sample files from the page sample captures for Wireshark. And it was 300 files, which had over 200 megabytes. So mostly those files were very big. But upon several months of coverage-guided fuzzing, I actually was able to first create a very good corpus, which consisted of almost 80,000 files. But the median file size was just 47 bytes. So they were really actually optimal for fuzzing. And if you want to test out your fuzzing infrastructure, Wireshark is actually a very good thing to do this on, because the nature of the code base makes it extremely well fit for dump fuzzing, because it has a vast number of dissectors for different formats. It's mostly written in C and operates on very, very simple data structurally. So it just mostly compares single bytes or some very, very simple constructs in the input file. So it's generally a very great test target for your fuzzer. And this is the trophy case for Wireshark in the Project Zero tracker. Also, this approach proved to be useful for Adobe Flash. So I've been fuzzing it for many years, not so much with coverage guidance, but recently I started targeting the ActionScript loader class. And in the official documentation, you can see that the loader class is supposed to only support JPEG, PNG, GIF, and SWF files. But when I was fuzzing this with coverage information, after several hours of fuzzing, I observed two sudden peaks in the number of coverage traces. And when I looked into the input corpus, I noticed that the fuzzer discovered two new signatures called ATF and II, which corresponds to a format that I didn't know before, which is called Adobe Texture Format for Stage 3D, which can have embedded JXR files. So these are two very complex file formats whose support was not documented anywhere, and I was able to discover this by just using this code coverage algorithm. And I found 7 vulnerabilities in those formats thanks to this discovery so far. So also, when it comes to corpus post-processing, if the files are stored in a way which makes them difficult to mutate, you can do some pre-processing, such as decompressing them. If they are compressed, for example, in SWF files, you typically have them in a LZMA compressed form, such as with the CVS signature. PDF documents also have most of the binary streams compressed with deflate, so you can also decompress them to make sure that the bit flipping makes sense. And also type 1 fonts are always encrypted with a simple cipher. So as several things about running the target and several tips. So we have to distinguish between command line and graphical applications. It's generally preferred, at least for me, for the target program to be command line only, which is quite common on Linux and less so on Windows. Most open source libraries actually ship with some ready testing tools, which are command line, which we can use for fuzzing. And this is much cleaner in terms of interaction, logging, and basically everything else in fuzzing. But there are also some graphical applications for Linux. in which case we can use the X virtual frame buffer to deal with this. And the thing is that for some applications, the amount of input data processed is actually dependent on the amount of data which is displayed on the screen, which is the case, for example, for Adobe Reader. And my solution for that was to just start a virtual X frame buffer with a very huge resolution, and then start Adobe Reader such that it would have a huge window displaying all of the pages at the same time. So this is the result. It was a very dumb way to make sure that as much PDF data was processed as possible, and it really improved the number of bugs that I was able to find in Adobe Reader. And it's interesting because Adobe Reader is supposed to be a graphical-only application, but if you start it from command line with the help command line argument, you can see that it actually has a lot of command line arguments. And while we're at Adobe Reader, I wanted to mention that I performed some fuzzing of it in 2012 and 13, which with some bugs found. But then in 2014, after Adobe Reader for Linux was discontinued, I still had some very better methods than before. So I still wanted to find some bugs in Adobe Reader. But I couldn't really use a new version because it was discontinued. So my idea was to use the Linux version and fuzz it on Linux and then see if any bugs would actually reproduce on the Windows version. And it turned out that I ended up with over 700 crashes in total in the Linux version, out of which 11 reproduced on the Windows version as well. And they were fixed in 2014 and 15. So when the program misbehaves, there are certain behaviors that are undesired during fuzzing. For example, we don't want to deal with some generic exception handlers which would mask the exceptions that we want to catch and stuff like that. They could attempt to establish some network connections, user interaction and stuff like that. And I have found that on Linux, it's very convenient to use the LD preload to actually block off some of the functions that you don't want to have called. So for example, you can disable custom exception handling by masking out two functions such as signal and sigaction, just to replace them with no operations. You can disable network connection by just masking out the socket function and stuff like that. And you can also think about fuzzing the command line for some of the targets. So some projects have multiple command line flags which you might want to flip randomly in order to reach some interesting functionality. Especially in open source projects. And the solution to that would be to have an external target launcher, which determines the actual command line to be used based on some data from the actual input files, and use that information to pick the command line to be used. So for example, we have FFmpeg, where you can specify the output format in which you want the output file to be generated in. And if you list these formats, it turns out that there is over 300 of them. So it makes sense to try to test all of them. And the logic for the wrapper would be to just choose the encoder based on a hash, which is generated out of the 4,000 bytes, the first bytes in the input file, and then execute such a command line. And another funny thing is that you should always make sure that you're not actually losing cycles, which was what I did. So this is an example of FreeType, which is a very convenient command line utility called ftbench. And it runs through 12 tests, exercising various API library calls. And when you run it with no special parameters, it takes 25 seconds, for example, to just process the file. And the important thing is the reason for this. You can see that it says number of seconds for each test equals 2, which I didn't realize at first. It didn't really strike me for a long time. And it turned out that you can use a special flag to actually just run every test just once instead of for 2 seconds. And this sped up the fuzzing by at least 100 times for me. But I was still able to find some bugs using this very slow fuzzing. So I'm afraid I have to skip through some of the slides here. I wanted to also talk about mutating inputs. You will be able to check out the slides later on. There were some interesting thoughts about, first of all, how to mutate the data, and also what ratios to use for those data, because you don't always want to flip a specific number of bytes, but you want to adjust it based on the nature of the input data. And then I also wanted to quickly talk about the Windows kernel font fuzzing effort. Maybe I'll try to talk about it really quickly. So I decided to do it in Box because I'm a very huge fan of it. It's a software emulator, and I've already used it for some projects. It's not very fast, but we can still scale against that if we use some more machines than just one. So it has some very useful properties. It can be run on any Linux system. It provides a documented instrumentation API. So it makes it possible for you to interact with the guest. It runs Windows out of the box, which is very simple, and you can easily configure it. So let's do it. When it comes to the input data, this part was the easiest one because I already had an input corpus of files based on free type 2 fuzzing. So what I only had to do is to extract true type and open type files because the other ones that free type supports aren't supported by the Windows kernel. So the part of mutating TTF in the OTF was the more interesting. I decided that the mutations would be applied in box instrumentation instead of the guest system itself, because it would be much faster that way. The question is how to mutate them properly to get the best result, because both TTF and OTF follow a common chunk structure called SFNT, in which each file consists a number of tables, which are publicly documented. So there are a total of about 50 tables in existence in total, but only 20 or so are actually important. And one thing they have in common is that they all are different. So they have a different length, different structure, different kind of importance for the operating system and the parser and stuff like that. So it only seems reasonable to treat each of them individually instead of fuzz the file as a whole. So the typical scheme I've seen in nearly every font fuzzing presentation would be that we just took the whole font and we would flip some bits in the whole file, and then we would just fix up the table checksums in the header so that Windows would actually accept it. But I decided to go a different way, and instead of fuzzing or mutating the whole font file, I would be fuzzing each of those tables individually, such that I would get the success to failure ratio at around 50%. So 50% of the time Windows would actually be able to process the mutated file correctly, and 50% of time it would fail, which would mean that we would be kind of at the verge of the mutated file being correct. So I just wrote a very simple program to actually determine what mutation ratio would be best fit for each of the tables and each of the mutation algorithm to maintain the 93% correctness. And this resulted in the following table of mutation ratios for each of the algorithms and each of the SFNT tables. So I also didn't set the mutation ratios to be fixed as shown in the previous table, but I also allowed some freedom in that. So I set a range between 0 and 2 times the mutation ratio that I determined. And with a trivial piece of code to disassemble, modify, and reassemble SFNT files, I was now able to mutate them in a very meaningful way, being able to control how they behave in Windows. I also wrote a very simple TTF generator with TTF instructions, which consisted of disassembling the TTF files, inserting new instructions with a Python generator, and then reassembling it back. And I managed to find one extra bug with this generator, so quite less than with just the dump fuzzer itself. And when it comes to the communication channel between the host and the guest, I used the box instrumentation to detect a specific instruction. In this case, it was elfence. And I used this instruction to implement operations such as request data, which would allow the harness in the guest to request mutated font data from the host, send status to send status whether the loading of the font succeeded or not, and a simple debug print. So of course I had to be very careful to be sure that all of the memory regions passed back to box were mapped in physical memory, so I would be then able to write to it directly. I also implemented a good harness to be able to get the best code coverage in the Windows kernel. So I would call all of the available API functions which were operating on the fonts, and I would list and display all of the glyphs in the font to make sure that all of the mutations would actually be triggered in the Windows kernel. I also optimized the operating system to the maximum extent. So I disabled all of the themes, disabled services that were not necessary, removed most of the system files, removed all items from AutoStart, disabled paging and stuff like that to make sure that the guest system was actually very quick and we wouldn't be losing any cycles inside of the box. And of course, I also had to make sure that the system would actually restart when the crash happened, so I could just detect a system reset as an indicator for a crash in the Windows kernel. And then when I wanted to reproduce the crashes, I would do it in a separate VirtualBox VM. I would just load the font in the same way as during the fuzzing and then check if there is a crash dump in the Windows directory. If so, I would generate a report from that and save it. I also did some minimization, but I won't really talk about it anymore. But the general result from this research is that I found all classes of bugs, basically, mostly pool-based buffer overflows, but also some overreads, use after freeze, and other interesting things. This was done in 4 iterations, and this is not necessarily the end. There could be more bugs discovered, let's see, in the future. So the closing thoughts is that hopefully after this effort, no more bugs are lurking in the Windows kernel, font processing. Let's see if that is the case or not. Either way, Microsoft has moved font processing into a user space process, which is good for security, but it could also make fuzzing easier for us. And yeah, we can still think about using it as an RCAE vector, because even though it's not anymore in the kernel, but in user space, we can still use it to get some kind of remote code execution. So with that, I thank you for your attention, and I'm happy to answer questions probably after the talk.